Let's discuss a little bit about a nice number game. Let's call in my office, nodding for mask. So let's call the four number game. So the idea is the following: we start with any four numbers. We can doesn't matter, but we can for simplicity we can take them positive. So 7, 19, 43, just make a random choice. So let's say initial sequence of four numbers. So from now on, any sequence of four numbers will produce a new sequence of four numbers by the following rule. So take the first two numbers and take the absolute value of the difference between those two numbers and put the result here in the first position. So this would be 12. So out of 7 and 19, 19 minus 7 is 12. And we'll put a number here. So we need only absolute value of the difference. So here we can get 21. Here we get 37. Now, when you get the last one, this sequence of numbers, it is assumed to be wrapped around the circle. So to the right of 7 is 19, to the right of 19 is 40, to the right of 40 is 3, to the right of 3 is 7. So everything goes back to 7. So now, what do I put here? Absolute difference between 3 and 7, which will be 4. Then continue. We iterate this construction. So 9, then 16, then 33, then 8, then 7, then 17, then 25, then 1, then 10, 8, 24, and 6, then 2, 16, okay, or get 18, and 4, 14, 2, 14, 2, 12, 12, 12, and then 2 minus 14 is minus 12, so we get a 12 here. And finally, 0, 0, 0, 0, and we stay there. So the point of this game is that no matter what sequence of four numbers we start with, eventually we'll get to 0, 0, 0, 0. Okay, how to prove that this happens? So theorem, let's put the following theorem. This four number game, this is called Ducci game, according to the person who allegedly invented this game. So the Ducci game eventually reaches 0, 0, 0, 0. Proof. Okay, so let's assume that we start with four numbers. So let's see, we start with x1, x2, x3, x4. So again, let's assume that all the numbers appearing in the game are non-negative integers. So let's assume that m is the maximum of x1, x2, x3, x4. So m is the maximum number on the first row of the Ducci game. So now let's assume that x1, x2, x3, x4 iterates, and we'll get here absolute value of x1 minus x2. Here I'll put absolute value of x2 minus x3, absolute value of x3 minus x4, and then absolute value of x4 minus x1. So if all the numbers in the first row, if the maximum is 10, then all the numbers in the second row, all of them are less than or equal to n. Because x1, x2, x3, x4 are all of them less than or equal to n. Okay, one of them is n, but in particular, all of them are less than or equal to n. If we take the absolute value of the difference of two numbers which are less than or equal to n, this number modulus of x1 minus x2 is still less than or equal to n. And the same goes for the second one. And it's still just for the third one, for the fourth one. So, assuming that the n is the maximum value of the maximum number in the first row, all the subsequent numbers appearing in the Ducci game are less than n. Because the second row, all the numbers in the second row are less than or equal to n. By the same logic, because all the numbers in the second row are less than or equal to n, we iterate again, and all the numbers in the third row will be less than or equal to n, and so on. So basically, if n is the maximum of x1, x2, x3, x4, then all the subsequent numbers appearing in the Ducci game are less than or equal to n. So what do we prove here? We just prove that if n is the maximum number in the seed means the first sequence of four numbers, then all subsequent numbers emerging in a Ducci game are less than or equal to n. So in a sense, this keeps the situation controlled. So all the numbers appearing in the Ducci game are less than or equal to n. Okay, like in the previous problem, the biggest number in the first row was 40. So all the subsequent numbers in the Ducci game are 40 or less. Okay, so that's the first important result. So all the numbers are bounded from above by a unique quantity, n. So let's call this lemma 1. So all the numbers appearing in the Ducci iteration are m or less, are between 0 and n. So the evolution of the Ducci game is controlled. Okay, now lemma 2. Lemma 2 involves divisibility properties. Okay, so lemma 2. After 4 iterations, all the numbers on that specific line are even. After 4 iterations, we get all even numbers. So remember the Ducci iteration: x1, x2, x3, x4 produces the following: modulus of x1 minus x2, modulus of x2 minus x3, modulus of x3 minus x4, and modulus of x4 minus x1. The key point here is for any two integers x and y, modulus of x minus y is congruent to x plus y modulo 2. So, for example, we have modulus of odd minus odd, right? Which is, we are looking at mode 2. Modulus of odd minus odd is 0 mod 2, but odd plus odd is 0 mod 2. Modulus of even minus even is 0 mod 2, but even plus even is 0 mod 2. Again, modulus of even minus odd is 1 mod 2, and even plus odd is again 1 mod 2. So in all cases, if we consider the remainder when dividing by 2, modulus of x minus y is the same parity as x plus y for any two integers x and y. So if we ignore the modulus and we only look at even slash odd, what will be the Ducci iteration? Starting from the, let's call the first line A, B, C, D. So only look at mod 2. So the next line will be A plus B, B plus C, C plus D, D plus A. Okay? The next line, we have to add these two. But remember, B plus B is a 0 mod 2. So what do I write here? A plus B plus B plus C, that's A plus C. Here I write B plus D. Here I write C plus A. And here I write D plus B. Okay? One more time. Here I get A plus C plus B plus D. A plus B plus C plus D. Next, A plus B plus C plus D. The same. A plus B plus C plus D. A plus B plus C plus D. And A plus B plus C plus D. But then, after one iteration, two iterations, three iterations, after four iterations, all those numbers modulo 2 are the same. So, have the same parity, or odd or even, because the same number. So, I get a 0, 0, 0, 0, but what kind of 0? 0 mod 2. So, after four iterations, we get even numbers. Okay, that was lemma 2. Let's keep the lemmas here. Okay, as a consequence, so how can I extend lemma 2? So let's consequence here. Let's discuss a consequence of lemma 2. So we have row 1. So after four iterations, we get, okay, let's call it row 0. So let's just to in accordance to time 0. So the beginning of the evolution. So row 4 of the Ducci game. In row 4, all entries are even. So this concurrent to 0 mod 2. Now, if they are concurrent to 0 mod 2, that means I can take a common factor of 2 and play the Ducci game with half of each number in row 4. So, which again obeys the same property. After 4 more iterations, I get another factor of 2 from all the halves of the numbers in row 4. So, after 4 more iterations, I get row 8, in which all entries in row 8 of the Ducci game are a multiple of 4. So, it will be a concurrent to 0 mod 2 squared. Okay, so let's see. Let's continue the same way. So, every entry in row 8 is a multiple of 4. So now, imagine I will give a 4 common factor and with the quotients play again the Ducci game. After 4 more iterations, we get another factor of 2 out. So after 4 more iterations, in row 12, all the entries in row 12 are congruent to 0 modulo 2 cubes. So all entries are multiples of 8. And so on. So what does it mean? In row 4n, so in row 4 times 3, all entries are multiples of 2 cubed. In row 4 times 2, all the entries are multiples of 2 squared. In row 4n, all entries in row 4n of the Ducci iteration are multiple of 2 to the power congruent to 0 modulo 2 to the power n. So we just proved that after 4n iterations, every entry in the corresponding row of the Ducci iteration is a multiple of 2 to the power n. So let's write down the consequence of lemma 2. Let's call it proposition 3. Which is an extension of lemma 2. After 4n iterations, we get any entry in the Ducci row is divisible by 2 to the power n. So after 4 iterations thereafter, so once we go past 4n iterations, the Ducci game contains only numbers multiples of 2 to the power n. Okay, so let's try if we can put together everything we got so far to get a conclusion. So for once, we know that all the numbers in the Ducci game are bounded from above. So all of them are at most n. On the other hand, we know that as we move on in the Ducci game, the numbers in the Ducci game, which appears in subsequent rows, are divisible by bigger and bigger powers of 2. So after 4n iterations or more than 4n iterations, all the numbers in any Ducci row is divisible by 2 to the power n. So what do you make of a number which we know that on one hand is bounded from above by n? What do you make of it if as the iteration goes by, at some moment 2 to the power n gets even bigger than n? So now, for some n, 2 to the power n is bigger than n. Right. So let's call it for some n0. 2 to the power n0 is bigger than n. So what does it mean? In the row n of the Ducci game, in row n of the Ducci game, every entry is divisible by 2 to the, so in row n, for every n greater than or equal to n0. So for every n greater than or equal to n0, in row n of the Ducci game, every entry is divisible by 2 to the power n0. So in row n, for every n greater than or equal to n0, every entry is divisible by 2 to the power n0. But 2 to the power n0 is greater than n. Right? Every entry which we know is less than or equal to n. If a number which is more than or equal to n is divisible by 2 to the power n0, which is greater than n, the only chance for that entry is to be 0. Right? So every number which is less than or equal to n on one hand, and divided by 2 to the power n0, which is greater than n, so on the other hand, the only chance for this to happen is that entry is 0. So let's put everything together. In row n, for every n greater than or equal to n0, every entry is 0. So once we iterate the Ducci game, after n0 iterations, where n0 is the first number which makes 2 to the power n0 greater than n, all the entries are 0. So this proves that the Ducci game eventually converges into a cycle of range 1, which is 0, 0, 0.